Good morning everyone, I am Jerome Suarez and I will be presenting a study entitled Automatic Detection of Spatial and Temporal Variation of Rice Planting in Laguna, Philippines. It is an output study of SIMS or the Saray Enhanced Agricultural Monitoring System of Project Saray. SIMS is a GIS and remote sensing based system that is capable of processing satellite data and converting them into a form that can help our LGUs and farmers in agricultural monitoring. When we talk about agriculture, we can think of a farmer with his ever-reliable friend, his carabao. Now, we want to introduce a new friend to him, the satellite. Unknown to the farmer, he is being watched by the satellite from above. And it's not only one, but many of them are looking at the farmer's field. Satellites can sense the type of crop planted, the growth stage, and the health of crop. We call this technology remote sensing, specifically satellite remote sensing. Now we can classify satellite remote sensing into two, passive and active. Passive remote sensing utilizes sun's electromagnetic energy by receiving the reflected sunlight of the surface. It's like an eye in the sky. It can give you a good picture of Earth from water to vegetation to build-ups. One major problem with passive or sometimes called optical satellite is that it is greatly affected by clouds. Once there's a storm or the sky is cloudy, this type of satellite becomes useless in agricultural monitoring because you cannot see the crop status under the clouds. And this is where synthetic aperture radar or SAR, an example of active satellite, is an advantage. It can take an image of Earth day and night in almost all weather conditions because it can pass through clouds. SAR sensors are not dependent of sun's energy, but rather they work by emitting their own energy and measuring the backscatter of the surface. SAR sensors are affected by surface roughness and wetness. Thus, they are best used in delineating water signatures such as mapping flood extent. They can also be used in determining rice areas in land preparation or land soaking stage. For this study, we use Sentinel-1 for SAR data and Sentinel-2 for optical satellite data. Sentinel-1 has two satellites, the Sentinel-1A and 1B. Sentinel-1A started its mission on April 2014 and Sentinel-1B on 2016. Its temporal resolution is 6 days with 10 meters spatial resolution. On the other hand, Sentinel-2 has also two satellites, the 2A and 2B, and have 5 days temporal resolution and also 10 meters spatial resolution with 13 bands including RGB and NIR for agricultural monitoring. And it started its mission on June 2015. For data acquisition, we use Google Earth Engine or the GEE, an online platform that collects and stores satellite images and geospatial datasets and lets you process and analyze those using JavaScript coding. The process of acquiring satellite data and pre-processing is fast compared to the traditional way of processing satellite data, where you need to download and process the data using GIS softwares. All processes are executed online with the use of Google supercomputers that helps you save time and space in your local disk because you do not need to download the raw satellite images and process it. There are petabytes of data available in Google Earth Engine such as satellite imagery, climate and weather data, atmosphere and geophysical properties of the Earth, and they are all available in script environment in just one click. We also use QGIS, a free and open source geographic information system for the processing of data. The study aims to demonstrate an approach to determine spatial and temporal variation of rice planting in Laguna using both SAR and optical satellite data. Specifically, it aims to determine areas in early and late transplanting and compare the computed and reported rice areas. The chosen area for this study is Laguna with 30,619 hectares of rice area according to the Philippine statistics, and most of the rice areas are located in the southern part of Laguna de Bay, specifically in the municipalities of Calauan, Bay, Victoria, Pila, and Santa Cruz. Methodology includes data acquisition and pre-processing of satellite data in Google Earth Engine and area computation in QGIS. Available Sentinel-1 and 2 images of the area for dry season planting were acquired. Sentinel-2 images were filtered to less cloudy and exported to QGIS for the computation of normalized difference vegetation index using the band 4, the red band, and the band 8, the NIR. NDVI values were plotted and analyzed to determine the start, peak, and end of season. The pre-processed Sentinel-1 images were also acquired using JavaScript coding in Google Earth Engine. Dual polarized VB and VH in interferometric wide swath mode ground range detected product was used. The RGB composite of Sentinel-1 using different months of data from the dry season planting was created, and K-means clustering was used to classify the RGB composite of Sentinel-1 and exported to QGIS to compute for the area. For the results, Figure 4 is showing the NDVI image of clear Sentinel-2 over the rice areas in Laguna. White to yellow areas signify low NDVI, which means there is no photosynthetic activity in the area or no vegetation. On the other hand, green areas have high NDVI value, signifying the presence of vegetation. The graph of NDVI from Sentinel-2 shows that they started to prepare the land on December with low NDVI. The initial stage of crop was observed on late December to early January with 0.3 NDVI. Then the peak was on February at almost 0.8 NDVI, and the harvesting stage was on April. For Sentinel-1, backscattering on water surface is very low. That is why it appears black in Sentinel-1 images. Now, looking at the rice areas in Laguna on December 26, 2017, we can notice that the rice areas are still in land soaking stage with very low backscatter value. This coincides with the low NDVI in Sentinel-2 images. Using different dates of acquisition, we can create a color composite of Sentinel-1 data. The color composite provides us a clear image of spatial variation of rice planting in Laguna. The color variation on the map shows that the rice crop is at different stages. The VH polarization performs better in determining spatial variation of rice planting in Laguna. The intensity of backscatter is affected by the changes in phenological stage of rice. From land soaking to initial stage, backscattering is low due to the presence of water. As rice crop grows, radar signal from the surface and canopy interior scattering are both received by the sensor, resulting to higher backscatter. The time series of Sentinel-1 backscatter show areas already in land preparation, while other areas still have rice to be harvested. The time series graph of Sentinel-1 backscatter shows the temporal variation of rice planting in Laguna. Different planting dates was observed in rice planting in Laguna even for two adjoining fields. There are many reasons for the variability of rice planting. This is maybe due to the availability of funds, water, labor, or good weather. However, the delay in planting reduces the potential yield and increases the risk of infestation. Determination of the best planting date to produce good yield greatly depends on the variety, crop requirements, and weather of an area. The ideal time may vary every year. The cropping calendar is necessary to determine the time and duration of farm activities as well as organizing the inputs needed in farming. Rice area from the color composite of Sentinel-1 image was computed and compared to the reported area in PSA and gained an accuracy of 89%. In this paper, the combination of Sentinel-1 and Sentinel-2 imagery for automatic determination of temporal and spatial variability of planting rice in Laguna was analyzed. The time series of Sentinel-2 NDVI and Sentinel-1 backscatter in VV and VH polarization shows the temporal variation of rice planting in Laguna. The sensitivity of backscatter intensities to water body enables mapping of early and late planting of rice. The color composite of Sentinel-1 provides us clear image of spatial variation of rice planting in Laguna. Combining SAR and optical data increase classification accuracy for rice.